Thanks everyone for joining today's Space Syntax Lab seminar. This talk is the first in our Term 2 series, where we will be exploring a range of topics, including Iranian kitchens and domestic life, inpatient ward design and care team communication, navigation and cognition in urban environments, and modeling retail activity through accessibility. Today, however, we will focus on the links between urban activity and social media. And I'm very pleased to welcome Linghao Wang, a PhD candidate in the Department of Architecture at the National University of Singapore. He holds a master's degree from Southeast University in Nanjing and a bachelor's degree from Wuhan University of Technology. His research approaches the city as a complex system with particular interest in street network analysis, urban morphology, social sensing, and the modeling of spatiotemporal activity patterns. And his current work investigates how large language models can be used to extract place semantics from social media data and how these meanings interact with urban centrality to shape patterns of urban activity. Through this integrative framework, his research aims to bridge urban morphology, data-driven methods, and human activity analysis, contributing to a more nuanced understanding of the relationship between urban form, place meaning, and urban dynamics. Before I hand over to Linghao, a quick note on questions. As usual, please feel free to post them into the chat as we go along, and we will address them at the very end during our Q&A session. And with that, Linghao, over to you.
Okay, thank you, Kim. Thank you for the introduction. And hello, everyone. My name is Linghao Wang, and it's a great honor to present our research at the Space Syntax Lab seminar and to have this opportunity to discuss with this work with you. Okay, without any delay, let's begin our presentation. The title of my talk is Exploring Urban Activity Intensity with Gravity-Based Betweenness Centrality and Social Media Evaluation, a case study of Beijing. To begin with, let me give you a simple example from Beijing. Imagine you are visiting the city and want to try Peking roast duck. You have two options. The first is Lichun restaurant on the left hand, which is hidden in a narrow alley with relatively low spatial accessibility. And the second one is Quanjude on the right hand. It is a famous restaurant located in Qianmen, one of the most central and accessible area in Beijing. So which one would you like to choose? Well, intuitively, I think many people would choose Quanjude because the building is visually prominent and the entrance is decorated with traditional Chinese architectural elements. And most importantly, it's easy to access. Well, but does this mean Lichun receive fewer visitors? The answer is no. In reality, Lichun is extremely popular online and enjoy a strong reputation for offering authentic and high-quality roast duck. During peak hours, long queues often forms, so we can see many people waiting here. And in this case, the disadvantage of less accessible location does not reduce visitation. Instead, its positive reputation on social media can compensate for its spatial weakness by actively attracting visitors. So I'd like to use this example to emphasize that the aim of my research is to understand the driving force behind urban activity intensity by jointly considering physical accessibility and intangible place evaluation derived from social media data. As we know, urban activity intensity is a key indicator for evaluating urban sustainability. Understanding its spatial distribution is fundamental to many urban planning objectives. Areas with high access intensity are often associated with more efficient land use, stronger economic vitality, and higher level of social interactions. It also provides critical insights for other sustainability-related goals, including carbon mitigation and urban thermal comfort improvement. Urban activity has long been studied through classic theoretical frameworks, such as Jack Booth's theories of street life, Kevin Lynch's concept of good city form, Hillier's space syntax, and Carmona's investigation of public space. These theories emphasize the role of built form, functional density and diversity, and accessibility of street networks in shaping urban activities. Among built environment factors, street networks are not merely a backdrop, but an active agent in shaping urban life. The relational structure of space actively generates and constrains patterns of human behavior. In space syntax, the core concept is spatial configuration, which means the way spaces are connected to each other as a system. Hillier argues that people intuitively respond to this configuration when choosing routes and activity locations. Measures such as integration choice and depth quantify how accessible or central a space is within the overall spatial network. And these properties correlate strongly with flows and land use. And this logic is extended by Yao Shen, and he proposed that urban centrality is not just a spatial property of a street network, but emerged from the interaction between spatial form and urban functions. In network analysis, betweenness centrality is a fundamental measure for evaluating a node's importance and modeling through moments within the network. In urban system, opportunities and resources are unevenly distributed. This has motivated extension of traditional betweenness to account for weighted interaction between origin and destination pairs. By doing so, betweenness can more effectively capture real-world pattern of human activity. For example, Salas incorporates population and employment in modeling urban dynamics. And at the street level, modified betweenness model have demonstrated high explanatory power for pedestrian movement. For instance, the series of work led by Professor Selfsuk. However, with the rise of information and communication technology, the traditional dominance of the built environment in shaping urban activity is increasingly being challenged by digital forces. Destination choices are no longer driven solely by physical accessibility. Instead, they are strongly influenced by virtual information, such as social media exposure. And ICT enhance virtual visibility while reducing the constraint imposed by physical distance. This shift has enabled more decentralized pattern of urban activity, where traditional commercial centers are experiencing decline and new business clusters are emerging in more peripheral locations with lower land costs and low accessibility. On social media, positive content such as favorable reviews and visually appealing images works as a recommendation. It increases visitation to highly rated places. As illustrated in the example I gave in the beginning, a restaurant located in a less accessible area can still attract a large number of visitors because of its strong online reputation. In this case, social media-based attractiveness moderates the effect of physical accessibility, reshaping urban patterns beyond what can be explained by built environment alone. And by leveraging social sensing methods to extract and quantify user-generated content, we can introduce an additional layer of influence into urban activity analysis. Therefore, the aim of this research is to enhance the understanding of driving force behind urban activity by incorporating both physical built environment and intangible place evaluation derived from social media data. To fulfill this aim, we propose a gravity-based betweenness centrality, the GBC model, to investigate the influence of social media evaluation. And leveraging this tool, we also explore nonlinear and temporal correlation between social media attractiveness and activity intensity. The study area of this research covers Beijing within the Fourth Ring Road, including approximately 14,500 street segments. The dependent variable is derived from Baidu heat map, a location-based service platform in China that provides hourly estimation of activity intensity at a spatial resolution of 170 meters rasters. Because of the limitation in data acquisition, we only select 2 ordinary days, 1 weekday and 1 weekend for analysis. And we further interpolate the raw data and spatially joined it to street segments using a buffer zone of 175 meters. The independent variables are derived from Chinese social media platform called Dianping. It is similar to Google Map reviews or Yelp. It provides users review and rating for places. In this study, we focus on 6 POI categories in Dianping, including business service, cultural places, drink, entertainment, food, and sports. We select these 6 categories because these are among the most frequently reviewed places and are closely related to people's daily life. And then the control variables are physical built environment data. And here I want to clarify the definition of street depth. It refers to the number of steps a street segment is away from major roads in the graph representation. Major roads refers to trunk, primary, and secondary roads defined in the OpenStreetMap. And the depth of a major road is defined as 0. And street segments with higher depth value are located deeper within urban blocks, indicating lower spatial accessibility. This figure illustrates the overall research framework. In the first step, we construct the GBC model and compute GBC values for 6 POI categories, together with the corresponding independent variables and control variables. In the second step, we calibrate the GBC model by evaluating prediction performance across 4 search radii using a random forest model. Based on this result, we select the best performing radius and conduct ablation experiments to assess the effectiveness of betweenness centrality and gravity mechanism in shaping urban activity intensity. In the third step, we interpret the result using explainable machine learning methods. Specifically, we employ shape value to examine feature importance, chains of correlation, and their temporal variation, and use partial dependent plots to investigate the interactive effects between GBC variable and street depth. In the GBC model construction, the first step is computing origin and destination weights. We start by associating POI points with street segments within the buffer zone of 175 meters. And the weight of each destination is represented by its attractiveness value. Specifically, for a given POI category on a street segment, the attractiveness value is calculated as a logarithm of the number of reviews multiplied by the rating score and then divided by the number of POIs in that category. The weights of origin segments represent the potential population that could be attracted to a destination segment. Because fine-grained population data acquisition is often costly or unavailable, so we assume that trip origins are primarily influenced by the proximity to public transport station, including metro and bus stops. And this assumption is based on official statistics in Beijing. The daily public transport trips account for over 50% of commuters. And the origin weights are calculated using an exponential decay function based on the distance to these stations. And the parameter beta and W are calibrated against hourly activity intensity to ensure the best correlation. The second step is to compute the gravity between origin and destination segments. The magnitude of the gravity depends on the three factors. The attractiveness of the destination, represented by dk, and the potential population at the origin, represented by OG, and the distance between OD segments. The third step is to transform the street network into a dual graph. In this representation, street segments are treated as nodes, and the intersections become the edges connecting them. In metric and angular distance, the edge weights are defined in meters and radians, respectively. And we compute both shortest metric distance and angular distance between node pairs using Dijkstra algorithm. The fourth step is to compute GBC value. Well, traditional betweenness centrality measures how often a given node lies on the shortest path between all node pairs in a network, normalized by the total number of shortest paths between each pair. The GBC model extends traditional betweenness in two ways. First, it incorporates a search radius following the bounded distance betweenness algorithm proposed by Brandis in 2008. And second, it integrates a gravity term between node pairs, inspired by the node weight accumulation algorithm in the UNA tool developed by Selfsuk and McConney in 2012. In addition, the GBC model supports two distance model, the metric betweenness, which minimizes the travel distance, and the angular betweenness, which minimizes directional changes. And these two formulations simulate different aspects of human route choice behavior. And to test the robustness of the GBC model, we established several baselines. First, we set the weights of origins and destination to unit value. That is the GBC-O and the GBC-D. So in this manner, we can remove the influence of OD weighting individually and allow us to isolate their respective contribution. And in addition, we include unweighted betweenness and the pure attractiveness model as baseline. So this comparison allows us to separately examine the explanatory power of the betweenness framework itself and the attractiveness components. And the control baseline, we only use control variables as influencing factors. Here comes the result. This figure shows the spatial distribution of GBC variables and their metric and angular distance. When angular distance is used, high GBC value are mainly concentrated along major roads. In contrast, under metric distance, higher value extend into deeper street segments within urban blocks. In terms of search radius, smaller radii produce more dispersed pattern, while larger radius lead to more continuous spatial distribution. This figure shows the calibration of search radius. For both weekday and weekend data sites represented by the dashed line and the continuous line, respectively, the optimal model are metric GBC with a search radius of 1,600 meters, achieving an R-square of 0.859 and 0.869 under five-fold cross-validation. Across both data sites, metric GBC model represented by red lines consistently outperform their angular counterparts represented by the blue lines. Based on the calibration results, we derive GBC variables within the search radius of 1,600 meters for subsequent analysis. And the result reveals a clear concentration in key subcenter of Beijing. For example, business service related GBC value are highly clustered in Guomao and Zhongguancun, which are well-known financial and technology hubs. Culture place related GBC value is mainly concentrated in historical districts such as Qianmen and Nanluo Guxiang, which are areas characterized by traditional Chinese hutong landscape. Meanwhile, drink, entertainment, and food related functions are strongly clustering in both historical urban cores and major commercial centers. This figure illustrates the ablation experiments, and the result is based on the R-square, MSE, and MAE across 20 random tests. And we can see that the GBC model consistently achieve a higher and stable performance. More specifically, the GBC model outperforms the GBCO, GBCD, and the unweighted betweenness, underscoring the importance of incorporating gravity mechanism between online attractiveness and the potential population. In addition, the GBC model also surpassed the attractiveness alone model, and indicating that attractiveness alone is insufficient for accurate prediction. Instead, the between centrality mechanism captures the diffusion of attractiveness through street network, and is essential for modeling activity intensity. And these figures shows variable importance in predicting activity intensity based on shape values. Looking at the difference of GBC variable, in the weekday data site, business service, sports, and drink function displays relatively high importance, while in the weekend data site, entertainment, culture places, and sports plays a more prominent role. To have a deeper understanding of the correlation between GBC variables and activity intensity, we examine the shape-dependent plots. In the weekday data site, all 6 POI categories show non-linear correlation with activity intensity, characterized by gradually increasing lowest curve, represented by the red lines. Although these correlations are generally positive, their overall influence is relatively moderate in magnitude. In contrast, in the weakened data sets, the positive correlation becomes stronger for culture places, entertainment, food, and sport. While the business surveys display a flattened trend. And in this pattern reflects a clear shift from work-oriented activity on weekdays to leisure-oriented activities on weekends. This figure illustrates the temporal trends of shift value for GBC variables. In weekday data sets represented by red lines, the temporal pattern suggests that urban activity is closely tied to utilitarian routines, with a higher shift value concentrated around business service, drink, and sports. So this indicates that under strong time constraint, people tend to prioritize socially attractive places that align with work and the daily schedule. Well, in weekends, shift pattern represented by blue lines, it reveals a shift towards leisure-oriented behavior, such as cultural places visitation, entertainment, and food-related places become temporarily more important in shaping activity intensity. This figure shows the interaction influence between GBC variables and the street depths. At the upper right region of the PDP plots, it represents higher street depth value together with high GBC value. And this combination represents lower spatial accessibility, but higher social media-based attractiveness. Besides, the red color in this region indicates a stronger intensity of human activity along these street segments. And across the figures, the red region is particularly concentrated in drink, entertainment, and food function. And it becomes even more pronounced and extended in the weekend data set. This pattern suggests that high social media attractiveness can mitigate the effect of low accessibility when attracting activities. And to validate the scalability of the GBC model, we apply the method to 3 areas in Nanjing, Shanghai, and Shenzhen, and they are all Chinese cities. These areas differs in urban context and network configuration. And we can see that the proposed GBC model can achieve higher R-square and lower MSE and MAE than their corresponding baseline models. And most of the performance differences are statistically significant. So far, let's summarize the main findings of this research. First, the GBC model outperformed baseline approaches in estimating activity intensity by integrating network centrality, gravity mechanism, and digital attractiveness. Second, the model operates primarily at a local scale, as the correlation peaks at a search radius of 1,600 meters. And the spatial distribution of activity intensity appears to follow the logic of shortest metric distance along street networks. And importantly, the result highlights the positive role of social media attractiveness in shaping activity intensity. And the prediction accuracy and variable importance are higher in weakened data sites, showing that online attractiveness has greater influence on leisure-oriented activities. And last, the PDP plots analysis demonstrates that high online attractiveness can offset the negative effects of low accessibility on activity intensities. In terms of theoretical contribution, the GBC model integrates a perceptual dimension into the street network analysis. It captures how digital attractiveness diffuses through and how potential population is transferred along street network, thereby reshaping potential distribution of activities. And this represents a shift in the role of betweenness centrality from a purely structural measure to a behavioral measure that reflects the influence of socioeconomic factors, such as social media evaluation. And therefore, we suggest that urban centrality is no longer determined solely by physical location. It has evolved into a hybrid construct shaped jointly by physical accessibility and digital visibility. In fact, the space syntax theory has enlightened our work, and in Hilliard's moment economy theory, spatial configuration generates moment and land uses. And subsequent studies have extended this framework. For example, Lerman and Omer introduce physical structure, and Yao-Shen propose the concept of functional centrality, and they all emphasize the influence of physical built environments or functional features in influencing human activity and socio-economic performance. And following these steps, the GBC framework highlights the role of social media evaluation in affecting activity patterns. And unlike physical built environment factors, social media evaluation serve as a virtual influences, often operating independently from physical environment. And we therefore propose adding a new dimension, place attractiveness, to interact with street network. And in this perspective, street network do not simply determine activity distribution, and they could act as a carrier that diffuse place attractiveness across space and scale. The GBC model has potential to support sustainable urban regeneration. For example, historical areas can introduce digitally attractive amenities such as cafe or cultural venues to enhance vitality while preserving existing urban fabric and avoid large-scale redevelopment projects. A business district can promote temporal mixed use by complementing daytime office function with evening leisure activity, helping to sustain activity throughout the day and improve economic efficiency. And underutilized space can be activated through pop-up uses, public arts, or co-working spaces, leveraging digital visibility and social media appeal to attract users. Of course, our research have some limitations. First, the analysis is correlational. While shape value provides insight into variable importance, it does not establish causality. And future studies could adapt causal inference method to validate the hypothesis in depth. And secondly, the origin weights proxied using public transport accessibility may not capture real-time population distribution. And thirdly, Baidu heat map data may be biased toward digitally active users and short-term activity dynamics. And fourth, future work can validate the GBC model across diverse urban contexts in different countries and extend temporal horizons. To wrap up, this study demonstrates that integrating social media evaluation with gravity-based betweenness centrality can enhance our understanding of urban activity intensity, especially in the information era. And the GBC model captures the interaction between physical accessibility and digital attractiveness, showing that strong online reputation can compensate for weak street accessibility, particularly for leisure-oriented activities on weekends. And these findings highlight the need for urban planning strategies that account for both physical and the perceptual dimension of places. By bridging spatial network analysis with digital human behavior, we can offer a more human-centered method for sustainable urban development. Okay, that's all for my presentation. If you are interested in this research and the code to fulfill the algorithm, please check out for more information in our paper published in the Sustainable Cities and Society. And thank you again for your attention and listening. And I would be happy to take any questions.